So we were talking about simple gas laws. We talked about Boyle's law, and now we're going to talk about Charles' law. Charles lived much later than Boyle. This is late 1700s, early 1800s. He studied the relationship between volume and temperature of a gas. And he found that the volume of a gas is directly proportional to its absolute temperature. So the temperature goes up, the volume goes up. So it can be stated this way: volume is proportional to temperature. We have to assume that the other two variables remain constant: pressure and amount of gas. So we can express it this way, but this is the most useful way: V1 over T1 equals V2 over T2. So that's one you need to know. What's very, very important is this word absolute temperature. This relationship only works if we don't have any negative temperatures. And so we always express temperatures for gas laws in kelvins, because the Kelvin scale has no negative temperatures. Here is a graph of Charles' law data. Here's the volume of a gas graphed versus its temperature. There are two temperature scales shown here. The top one is degrees Celsius. So the blue, the purple, the green, these are different sets of data for different samples of gases. And we see that there's a nice linear relationship. Remember that the equation for a line is y equals mx plus b. Well, on this graph, y is volume. So the volume equals the slope, m, times x, here x is the temperature, plus an intercept. This equation is complicated if the y-intercept isn't 0. If we look at these lines, they have different slopes, but if we extrapolate, if we draw the line past the actual data, we find that they intersect at a point. That point is called absolute zero. It's a theoretical temperature at which the volume of a gas would be 0. Now, obviously, the volume of a gas cannot be 0, but still, the data extrapolates to that point. This is the basis for the Kelvin scale, making 0 the temperature at which a gas has 0 volume. And so that happens to be 273.15, absolute 0. So when we use the Kelvin scale, then our intercept is 0. And so our equation is more usable. Let's look at what's happening with the particles in the gas. This is just something you could try at home if you're so inclined. Fill up a balloon with some air and stick it in ice water. As the ice water cools the molecules in the air, they're going to move slower. And when they move slower, they impact the walls less frequently and less strongly. So the force is lessened. The pressure decreases, the balloon shrinks. You stick that same balloon into boiling water, the molecules heat up, they move faster, they're going to hit the walls more frequently, they're going to cause an increase in pressure, they're going to take up more space. So the volume increases when the temperature increases. When the temperature increases, the gas particles move faster. We have more frequent collisions, and the force exerted with each collision is larger. If the pressure is going to be constant, and that's what the Charles law says, we're going to hold the pressure constant, then the only way for that to happen is for the gas to be allowed to occupy a larger volume. Yeah, we're running short on time, so I'm going to skip that one. Let's do a calculation. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? Okay, this is a relatively straightforward gas law problem. There's numbers in there among the words, and the numbers generally are important. So I'm going to show you how to make a table to organize those numbers. So with these simple gas laws, we have things that are changing. What's changing in this problem? The temperature. So we took this gas and we increased the temperature. There's a condition 1 and a condition 2. Doesn't matter which one you label them. They're not necessarily initial and final. I tend to just go along, and whatever number I come to first, I'm going to call that initial. So here, initial volume of 88.2. So I'm going to write that down in row 1, if I can remember how to write. 88.2 milliliters. And then I need to label the column. That is a volume, so I'm going to label this column V. I'm going to put all my V's in the same column. Then I go along and I go along and I find another number. So here we're heating the gas from this temperature to that temperature. This was our initial volume. This is our initial temperature. Those two go together. Make sure you get your numbers paired up correctly. So 35 degrees Celsius. And then the second temperature is 155 degrees Celsius. And I'm going to label this column T because these are temperatures. Can I do this with temperatures in degrees Celsius? No, we have to convert to Kelvin. So the conversion is that Kelvin equals the Celsius temperature plus 273.15. I'd like you to put the 0.15 in there. The book is sloppy. They use 273 a lot. I'm going to use 273.15. So if we take our 35 degrees and we add 273.15, we're going to get 308.15 Kelvin. And let's keep track of our significant figures. When we're adding like this, this temperature was to the nearest 1 degree, so this temperature should be to the nearest 1 degree. And then I need to convert the other one as well, 155 plus 273.15, 428.15 Kelvin. Both of those temperatures have 3 significant figures. I have a blank in my table. It's in column V, row 2, so I'm going to call that V2. Very creative. What is the final volume? V2 is the final volume. So we need to use a simple gas law equation, plug these numbers in, and find what V2 is. So this is going to use Charles' law. V1 over T1 equals V2 over T2. My experience is that many students don't remember algebra very well and have trouble rearranging equations. This equation has fractions in it, which causes even more problems. So what I recommend, unless you're a whiz at algebra, cross-multiply to get rid of the fraction and then rearrange the equation. And do all of that before you stick the numbers in. So cross-multiplying is going to give me V1 times T2 is equal to T1 times V2. And I'm looking for V2, so I'm going to divide by T1 so that I can get V2 all by itself on one side. If you struggle with rearranging equations, please come and talk to me. I can help you. Okay, so there's my equation. V2 equals V1 T2 over T1. Careful when you copy stuff down because it's so easy to put the wrong number or letter in there. So now I need V1, and I go to my table. It's all listed there for me. So V1 is 88.2. Always write the units. And T2 is the 428.15 Kelvin. And then T1 is 308.15 Kelvin. And then I'm going to look at the units, and I'm going to see that kelvins cancel kelvins, and the unit that's left is milliliters, and that's good news because that's a unit of volume, and it's even the one that the question's asking for. So now I use my calculator. 88.2 times 428.15 divided by 308.15 equals. How many sig figs should my result have? 3. So 122, there's my third significant figure. I'm going to write down 2 extras because that's what I do. And then I'm going to round this, and the answer will be 123 milliliters. You need to be able to show your work when you do these problems. On the exam, there will be a problem with a gas law where you have to show your work. So I'm going to tell you right now what I want to see as showing your work. Okay, inside the blue box, that is the minimum that you should write out to show your work for a problem like this. You have rearranged the equation. You've written the rearranged equation. You've written it with the numbers and their units put into it. Here's the unrounded result and the rounded final result. That is showing your work. We should also look at problems like this and ask ourselves, is this answer reasonable? We took a gas that was 88.2 milliliters and we heated it up. Do we expect the volume to be larger or smaller? Larger. It is larger. That's a good sign. Doesn't prove I did it correctly, but it's encouraging. If it got smaller, I need to go back and look and see what I did. And what would probably have happened is you got these 2 temperatures reversed. Really easy to do. Any questions? Another simple gas law, Avogadro's law, relates volume and moles. So the volume is proportional to the amount of the gas. That makes sense, right? You put more gas in, the volume gets bigger. What's not obvious is it's proportional to the number of gas molecules or atoms. The number of particles is what determines the volume. So Avogadro's law, constant temperature and pressure, the volume is proportional to N. N, the number of gas molecules. We use moles because that's how we count gas molecules. So Avogadro's law, another one to remember. V1 over N1 equals V2 over N2. Equal volumes of gases contain equal numbers of molecules. The identity of the gas doesn't matter. Doesn't matter what gas it is. Does that bother you? It should kind of bother you, I think. Because with liquids and solids, what the substance is matters. It's going to affect its volume. We'll talk more about that in a minute. So here's a graph of data. The volume increases as the number of moles of gas increases. And if we extrapolate back, we see a prediction of 0 volume with 0 moles of gas. Well, that seems pretty reasonable. If you have no gas, it would have no volume, okay? Oh, shoot. I thought there was more talking. The reason that the gas doesn't matter is that there's so much space between the molecules in a gas. Lots and lots of space. So the actual size of the particles doesn't matter. It's the number of them that matter. Okay, let's do an example of this. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperatures and that the initial amount of gas completely reacts. I don't particularly like this problem, but it's in the book, and I've decided to do those problems, and so we're going to do it anyway. This is not as straightforward as the previous example we did. So we have a chemical reaction occurring in a cylinder. So let's just kind of sketch that out a little bit. So we've got reactants. It's not a very good C. Reactants. And those are forming products. They don't tell us exactly what they are, but sometimes it helps to write something down, kind of sketch out what's going on, to help you see in your mind what's going on here. So we've got a cylinder with a movable piston. Okay, it says it produces 0.621 moles of gas product. So that tells me at the end I have 0.621 moles of gas. And it says the cylinder contained 0.12 moles of gas before the reaction. So before was 0.120 moles. After is 0.621 moles. Everybody okay with that? So let's make a table again, because those tables are really useful. So if I'm just going along, I come to this number first. I'm going to stick that in here, 0.621 moles. And then I'm going to ask myself, well, in the gas laws, the P, V, N, and T, what letter would this be? N. N for amount of gas in moles. So this column is N. And then I'm going along and I come to this amount, this many moles. Okay, so that also needs to go in this column. And that's the moles before. And so now I have before labeled 2 and after labeled 1. That's okay, because they're not implying first and second. They're just different. And then we have this volume. Which one does the volume go with? It goes with the 0.120. The cylinder contained this before the reaction and had an initial volume of this. So those two go together. Regardless of what we call them, 1 or 2, they need to be together. And some problems like this one, it's a little harder to identify which ones go together. Then they're asking for the volume after the reaction. This is my volume column, and so this is V1. So I'm going to solve for V1. I need an equation that uses V's and N's, and that's going to be Avogadro's law. V1 over N1 equals V2 over N2. So cross multiply, rearrange that, solve for V1. V1 equals N1 V2 over N2. Another way to look at these is I can take something from the bottom on this side and just move it to the top on the other side. That's all I did when I rearranged this. I took N1 from the bottom and moved it over. If you move it to the other side, it has to go on the opposite side of the line. If I wanted to move V2, it would have to come down. If that doesn't make sense, cross multiply and then rearrange. So I've got my equation, then I'm going to plug in my numbers. N1 is 0.621 moles. Always write the units. Volume 2, 2.18 liters. Divided by N2, 0.120 moles. And we see that moles cancel out, leaving us units of volume, which is good. So I've got 0.621 times 2.18 divided by 0.12, 11.2815. And the unit would be liters. How many sig figs? 3. So 11.3 liters. Is it reasonable? Which had more gas, before or after? After. This one has more gas, so we expect the volume associated with that one to be larger, and it is. Good. Questions? Another example. If you need some simpler examples of these gas law problems, go to one of my 3A playlists on YouTube, because the 3A examples are simpler. These require a little more thinking, which means that you have to be able to do the gas law really well so that you can focus on thinking. So this question is a little trickier. A scale model of a blimp rises when it's filled with helium to a volume of 55.0 decimeters cubed. When 1.1 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. Well, let's just put the numbers in a table. Because you maybe look at that and you're like, I don't know about that. Well, you got to start somewhere. So start by organizing. So 1 and 2. First number is 55.0 cubic decimeters. And what variable is that? That's volume, so that's V. And then I've got 1.1 moles of helium, and I've got another volume. I need to make sure I get that moles with the correct volume. So I'm going to do this one first, 26.2. Because that has to go in the volume column. Which volume does the 1.10 moles go with? The second one, the 26.2. When we add this much helium, the volume is this. Those are together. So 1.10 moles right in there. And that's N, because that's the variable for amount in moles. So then just looking at my table, I could figure out what N2 is, right? I might still be bothered by the question and the thing about adding grams, but hey, I could figure out N2. I'm just going to do that. So Avogadro's law, V1 over N1 equals V2 over N2. And this is the sort of problem, solving for something in the denominator, where students lose their heads. And you end up solving for 1 over N2. So what I'm going to do, rearranging in my head, is I'm going to put this one on the top and that one on the bottom, and I'm going to move that one up. It's not voodoo magic, but it kind of looks like it. So I'm also going to do it out the long way over here. Cross multiply. So I'm going to get V1, the top of one side, times the bottom of the other side, will be equal to the bottom of the first side times the top of the other side. And then I want to solve for N2. So I divide by V1, so those cancel. And I divide by V1. And there I've got this. Okay. So now we plug in the numbers. N1 is, I did that again, dummy. Okay, so what did do you see what I did? I called this N2. Okay, so I don't want to rewrite everything, so what I'm going to do is I'm just going to change these numbers. And this is going to be row 2, and that's going to be row 1, and then my equation's okay. You like that? Good grief. Okay. Everybody makes mistakes. 1.10 moles. And then I want volume 2, 55.0 cubic decimeters. And I want to divide by volume 1, 26.2. The cubic decimeters, which are kind of an annoying unit because we don't use those very much, those cancel out. 1.1 times 55 divided by 26.2. So this will also have 3 significant figures. So 2.3092 moles. That's not my final answer, because the question is, how many more grams of helium must be added to make it rise? So we calculated something, now we have to figure out how to get the answer from what we calculated. What did we calculate? What is the significance of this? This is the moles of helium that are in the blimp when it begins to float. This is the volume at which the blimp will begin to rise. And so we calculated how many moles of helium have to be in there for it to rise. You okay with that? Yes?
I must not be seeing it or something, but how is the 55.0 not the V1?
Well, if you're going in order, it would be V1. But I labeled this wrong, and then I rearranged this according to labeling this N2. And so what I did is I switched these numbers instead of having to switch all of those numbers. Yeah. So that's a very good question. I'm sure several people were wondering what the heck is up with that. But this is the amount of helium in the blimp when it starts to rise. But the question is asking us, how many more grams of helium do we have to add? So we've got 1.10 moles in there. How many more grams do we have to add? Well, could we figure out how many moles we need to add? This is the number of moles we need to end up with. This is the number of moles that's already in there. So if I subtract 1.10, I'm going to get 1.2092 moles. That's how many I should add. You see that? And this is the sort of thinking that you have to be able to do on an exam. You're not going to see a problem exactly like this, but you might see one that's going to make you think in the same way. Okay, so now I've got moles of helium. I need to make it into grams. And so I'm going to take the moles and multiply by the molar mass to get the grams. So 2092 moles of helium times the molar mass of helium, which is up there on the periodic table, 4.003 grams per mole. Oops. 1.2092 times 4.003. So 4.8404 grams. So we need to add 4.84 grams of helium to this partially inflated blimp to get it to rise. Any questions?